Yeah, you can start, Deshna. You can start.
Okay. All right. So good afternoon, everyone.
There, you can please put on your video. Your video is off. Yeah.
Yes, on my video. Yes. Can you see me?
Yes, we can see you.
Yeah. Okay. So would be of course curious to know if some of you had a chance to work through the kind of steps that we described yesterday. Has anyone taken a photograph of sort and tried a two-dimensional Fourier transform on it?
Yeah, there's somebody. Just a minute. You did something? Then please tell.
So, sir, with
Yes.
going into the same lines with Fourier transform, I thought
Yeah.
of doing not doing only on the clouds, but can we take crab picture and probably try on that?
Okay.
I was trying that, so I'm in the middle of somewhere. So if something comes up, I'll get it.
Okay. Yeah, maybe you can share that with others.
Sure.
You can tell.
Sure, sir.
You did something. Then come and say. Say something. At least you can look at somebody else. Are you on that side? Once again.
Hello.
Yeah. Yeah,
Yeah.
please go ahead.
As you asked, I took an image of the cloud.
Okay.
I don't know if it is visible to you.
Yeah, I can sort of make out.
Yeah. So I took an image of the cloud and got a magnitude spectrum.
Okay. Yeah,
And
you should get the power spectrum. That means modulus square, amplitude square. Okay.
yeah, I got a radiance
Yes.
profile of the power spectrum.
Yeah. So that can be averaged because that's an entity which whose properties are known. And so did you try doing an azimuthal average along a ring?
I did a frequency distribution plot just there.
Okay. So it's a 2D plot that you have, right?
Yeah.
Correct. Okay. So yeah, thanks for doing that. And maybe you can show it to others if, at least in whatever way it's possible there. Anybody else has tried out anything?
So some of them have done that basic plot.
Okay.
The fuzzy one which you get.
Yes.
People have done that and they didn't do more. Because Najam has done much more, but he'll share later. Yeah, these guys have done that.
Okay.
Yeah.
So let's other subsequent steps clearer to you, or we should revisit them. What is the general?
Sorry, once revisit, a short revisit, and then proceed. Yeah, that's the whole.
All right, so let's visit them. Fortunately, I found a small report come PPT that 4 of the students who took up this kind of an exercise from 2 of them from the Pune University and 2 from Ferguson College, undergrad students, who actually were enthusiastic enough to play with the kind of procedure that I have described. And they even presented that in one of the RAWS meeting at Ayuka. And I was trying to look for their presentation to sort of, show you an example of what all can be done. And I'm going to bring that up shortly. So let me see, share screen, start sharing, and let's see. Okay. So of course, this PPT has a whole lot of background about the FFTs and so on, which you do not require. But in terms of the two-dimensional structure, what all we are trying to consider as the basis functions whose grand superposition leads to the picture we have at hand is demonstrated here. It's sinusoidal in one direction, and another direction is constant at the value at which, so it's like, the kind of things which are shown here. So we're trying to look for superpositions of this. So essentially, if you just look at the sine of one component, Fourier component, which is along, let's say, the kx, has a certain kx value, then how will it look in kx and ky is shown here. Sorry, not kx and ky, x and y. And then it will correspond to a single point in kx with ky is equal to 0. So these are simple examples. They even took a picture that is shown on the left and Fourier transformed it. And of course, various streaks corresponding to the linear structures seen here are very clearly visible. Then they went on to take a cloth where there is a repetitive pattern. And as you can see, it's not really properly uniformly stretched cloth. And of course, the pattern, although it's nice and uniform grid, it will not appear like that in this picture. And the distortions of that will show up. So they have shown that, if you take the Fourier transform, you can actually see specific increases in certain locations, which can be understood in terms of the fine thread spacings. And to really see the spacing of these broad bands, the check structure, you really have to zoom into the center, and that's where you see this contribution. So you can actually, even work out how many threads, per centimeter or something, whatever, once you calibrate by using this as a much accurate measurement. Now this is about the azimuthal averaging. So what one is trying to ask is, please ignore the labels on the x and y axis. They are just the sample number in other domain, the Fourier domain. The origin really is where it's shown, which is the centers of these circles. And what is on one side of that origin is the negative frequencies along x-axis, and what is below the central horizontal line is the negative frequencies associated with the y-axis in the y direction. So these are basically the four quadrants that are being seen, where the frequencies are positive in the right top corner sector. So what generally we would get in the case of the random distribution, as against the very systematic picture pattern that you saw in this picture, is the mean intensity will be constant roughly as a function of the distance from the center. And although a particular realization of it at any given angle along a particular distance, along a circle of a certain radius, will vary, although it follows the same mean. And so we would like to get closer to the mean value by averaging whatever information we might have along an azimuth. By azimuth, I mean this going along the circumference of this circle. And so you can put a small range of delta r at a given r and ask whatever points are there inside that, they can be averaged together to get one value, which you tag with that r tag. You do that for every annuli. And then plot, then it becomes a one-dimensional information, which, so this will come to later. So what you will get is basically an information where spatial frequency and the power will be seen varying in this fashion. Now, based on the context, you would like to represent it in different ways. For example, if there is a random distribution and the underlying process has a sort of essential self-similarity in the structure, then you would expect some fractal dimension associated with it, which will define the slope of the power as a function of spatial frequency, where for a constant slope, you need to view that in log of the power versus log of the frequency, since the power depends on some fixed power of the spatial frequency. So the power index will come out as a slope. Many of these you will find have spectra which have more power at lower frequencies and less power at higher frequencies. These are generally known as red spectra. Many of the processes follow this kind of a description in the Fourier domain, and one would like to study them and to see what the underlying process, like the turbulence, is driven by, and how what are the key assumptions or key things that dictate the way the turbulence cascades from big scales to small scales. And as I said, for incompressible fluids, the Kolmogorov-like description is expected. Now, of course, here, if you do this azimuthal averaging, you will find that there will be peaks seen at different locations. You can also use that to plot either the average, which is not a great thing to do, because along any circumference that goes through these bright points, any circle that goes through these bright points, the rest of the points are contributing nothing, and you will unnecessarily dilute the information. That's why I would recommend generally plotting not only the information, which is the average, but also the maximum and minimum as a function of the radius. And that will give you many times the information which might get diluted otherwise if it's coming from a very specific pattern. So these are just the examples. For example, in that pattern that you saw, you will find the average is not really showing much, but the maximum along the circumference, if you plot that separately, it will show you a specific radius at which these points occur. So I recommend always these three entities to be plotted as a function of radius. One is the average, which we have discussed, and which is what will give the essential information in the cases of random patterns. But in case of specific patterns, the information or the contribution might exist only at few points whose contribution need not be diluted through the azimuthal averaging, and hence a max, the plot of maximum found along the circumference at any given radius would do very well. All right. Any questions?
Any questions?
You can proceed.
All clear?
Hello.
Yeah.
Everything seems to be clear. You can proceed.
Okay. All right. So the next thing is, for example, if you take pictures like this, you will find that there is no preferred direction or preferred orientation or elongation of any significance here, right? Whereas if you look at a cloud cover, for example, close to the horizon, if you take a picture close to the horizon, you will find there is a lot of projection effect, because of which the clouds might appear like elongated along the horizon line, and basically they are compressed in the orthogonal direction, as a along the elevation, because of the projection. Now, certainly that kind of picture will lead to a Fourier domain description, which will also carry this imprint of preferential elongation along the certain direction. And that can be also probed, and that will disturb our basic assumption that we assume that the contribution is essentially following the same mean along a particular circumference of a given radius. That assumption will not be valid, because now things are not azimuthally uniform. That means there is no cylindrical symmetry. The lack of cylindrical symmetry, which you can call anisotropy of some kind, can be probed by using another kind of averaging, which I think it's mentioned here. So let me. Which is a radial averaging. That means you can take sectors of certain angular width and you average or integrate the contribution in that entire sector of certain angular width, and then step through different sectors together spanning the entire 360-degree span, and then based on the sector orientation, which is changing through this full cycle, you can plot what the sum or the average looks like. And that's will give you an azimuthal profile. This azimuthal profile will certainly show you any deviation from the lack of circular symmetry or cylindrical symmetry. So this together with the azimuthally averaged information is a sort of a distilled version of two 1D descriptions, which summarize largely most of the stuff that is seen here in this 2D diagrams. It just becomes simpler to view them and extract information from them. Certainly in the case of random distributions, this amount of information suffices. And so I would encourage you to do again, along with the mean or sum, a plot of the maximum found, okay, and the minimum. So these two together, along with the basic average profile, either in azimuth or azimuthally averaged description as a function of radius, or radially averaged description as a function of azimuth, give you a lot of information. So I encourage you to do that, and even try out, not just keep limited to the clouds. You feel free to take patterns of your choice and see how things appear. The important thing that you will notice is something that is broad in the image domain has a narrow contribution or towards the low spatial frequency, and vice versa. Something that is narrow in the image will actually have an extended spread in the other domain, or might sit at a large offset from the origin. Any questions?
All's fine.
Okay.
Yeah, I had a question.
Yes.
What if you don't have nebulous objects? What if you have point sources, an image with point sources or something like that? How would that vary? Do you need to find something in extended objects, or can you even do with point sources?
Yeah, you can do it with any distribution, okay?
Okay.
But you can ask, so one of the things, let me state it, we normally say, use something and then go and Fourier transform it to see the same information represented in a different way, right? Now, why do we even bother to do that? We might want to do that because the information might be more compactly described in the other domain. And more compactness and energy conservation bind together ensures that whichever domain in which you have compact description, the volume under that feature, that base, associated with that base is going to be the same. So the feature with compact base is going to be always taller, and that is the key to using to deciding which domain we should go and look at things. If you have set of point sources, they're already compact and they have the best contrast in the domain in which you have the image. You need not go and spoil the contrast by taking its Fourier transform, unless you're looking for some pattern in the arrangement of those point sources, which might get probed better in the other domain. Okay.
Okay. Okay.
I normally, whenever I talk of uses of Fourier transforms, I would like to normally call it uses and abuses of Fourier transform. So there is no compulsion to take a Fourier transform of something that is already in the most compact form. Okay.
Okay.
You would go to the Fourier domain to appeal to more compact description of something, or some more insight, full description that might come through.
Yeah.
Unless there is a appeal like that, there is no reason to take a Fourier transform.
No, because I mean, one of the applications we were directly thinking of, for example, is if you have a galaxy image which you're trying to characterize using the Fourier this thing, right?
Yes. The
That's in
galaxy
principle
image
what you do. Yeah.
might have its advantage. The galaxy image might have its advantage because some of the features, for example, the spiral arm patterns and so on and so forth, might, the average separations between them might lead to a more compact feature in the Fourier domain, which will allow you to measure the average distances instead of painstakingly taking, separations between different arms and averaging them.
That's right. Yeah. So I was just thinking that how does it change if your galaxy is like a mix of nebulous as well as point sources and things like that? But I think that can work. It can be done, right?
Yeah, they can be. For example, when it's completely, what should I say, random distribution, right? You will find in the other domain also there is random distribution, but there might be some confinement of the scales, which, like in the cloud case, right?
Yeah.
And immediately getting the information about the contribution of the relative corrugations due to small scale variations in a cloud versus the broad scale, you will not be able to separate out just by looking at the picture. And this will give you a quantifiable description in the Fourier domain by separating them out.
Yeah.
And the behavior of the contribution at different scales will give you an idea of what underlying process might be driving such a structure.
Yes.
So those clues can be gotten, which are not readily forthcoming from the direct images. For example, even in this picture, you wouldn't be able to count the threads, right? In each one of these bands, which is readily done by the Fourier transform. If you measure one of these, you will find some of them correspond to the distance between along, parallel to the grid axis, and the other ones correspond to the sort of diagonal distance between the joints. And so these are nicely relatable, and you can see how quickly you can make a measurement of. Now the spread in these features, these not being a dot, but having some finite width, also shows you the level of uniformity, the wrinkles and so on, the role of them. Fuzziness can also be used to spell out how stretched it was, how nicely it was following the pattern or not.
Thanks.
Okay.
Yes, thanks.
Any other questions? Okay, if not, then I'm going to take you to something else which you would not have anticipated necessarily as a part of this discussion. But before I impose it on you, let me ask you, would you be interested? Would you be interested in knowing how to generate random patterns following certain statistical description, which you can use to perform various experiments. For example, if you would like to see how a random phase screen due to atmosphere or ionosphere or any other medium on the way that you encounter in astronomy context can be generated. If you wanted to, test out some of your ideas and you needed a situation where there is a random screen, random enough that how would you go about it? Would you be interested? If you were to be interested, this will help you to close the loop of, instead of relying on an image and then inferring things from there about which you know nothing about a priori what you should expect as an answer. This will, one person can generate such a screen or a picture, and then somebody else can push it through their processing chain for doing the kind of stuff that we described and see whether the answer matches with what was actually put in. Priya, do you think it's worth describing or it's not necessary?
Yes, ma'am, please say yes, because he was asking that. He was asking whether
I have to answer, no?
we can.
Yeah, please answer.
Yes, sir. Everybody was telling, but everybody is sitting in chairs. So yes, please.
Okay, all right. So I will. Okay.
And some people is requesting to repeat last part.
Okay. Which last part? The.
You need to come down.
Some people.
I'm so sorry, sir. Actually, I could not follow the question you were asking. That we are interested on.
Is the following. Right now we have gone this way where we have a picture to begin with, right? And we have seen what analysis can be done, okay, using Fourier transforms, and how information from that can be extracted in, by using one-dimensional pieces of information, namely azimuthal averaging, right? And radial averaging, right? So this will be a function of, once we azimuthally average, it will be a function of R, and this will be a function of azimuth, right? This part you understood?
Yes, sir.
Okay. Then I said that you have certain picture and you do something and you get these information. You have no way to verify them unless these are tied up with something like the cloth pattern and so on, where you can have some judgment of whether it appears correct or not. For a random distribution, you wouldn't know whether you got the answers correctly or not. Particularly in the case of, let's say, the cloud, because there's no prior expectation given to you. So to help in that regard, as well as to empower you to have the ability to simulate any distribution, random realization following certain spatial spectral description. Would you like to know a way of generating various realizations which you can use in great simulation studies that have various contexts, or at least in your present exercise as a starting picture whose properties and how it is generated is well known because you have generated it yourself. So my question was, would you like to know about how to generate a random distribution which often one encounters when one is looking at the electron density distributions in random media, or the refractive index variations or things like that. So that was my question.
Yes, sir.
Okay. So now what we're going to do is exactly use this understanding to generate that. Okay. So if, for example, you wanted to generate a description which follows certain power law. So this is K, log of K, and this is log of power, right? And suppose the slope there is alpha or minus alpha depending on. So let me write that very clearly. P is equal to some constant, right? P naught into K to the power minus alpha, where alpha is a positive entity. Slope here is negative. How do you generate a random pattern following this? What we said is, when we have a random distribution and when we take the Fourier transform, you will find that there will be Hermitian symmetry, but the real and imaginary parts will follow Gaussian distribution, and modulus square of which will follow an exponential distribution. And we're going to use this piece of information. If you look at the phase, which is the imaginary part, if you say tan inverse of imaginary part by real part, this will give you some kind of a phase associated with the complex number. And this can be shown to have uniform distribution between 0 to 2 pi. Okay. So the real and imaginary parts follow Gaussian distribution, and the phase follows uniform distribution, which simply means that the real and imaginary parts are completely uncorrelated with each other. They have no relationship between each other. They are independent Gaussian variates. Okay. So this is what we're going to use. Okay. So the recipe is very simple. You start off with the contribution, right? The F as a function of Kx, Ky is going to be what? Typically is going to be a complex number whose amplitude is square root of the power, right? The power exactly will depend on actual value of, the real and imaginary parts, but only statistically. So if you take two random numbers A and B, which are Gaussian variates, so you generate two random numbers and put them as real and imaginary parts of it, of the spectrum at any given kx and ky. Let their standard deviation be same and the mean to be 0. So same standard deviation and mean 0. So if you have that, then you will find that you can write the number as A plus I or J times B, right? And if, without loss of generality, if you make that unity, the standard deviation, then you can multiply this by the k to the power minus alpha by 2. What have we done? We want the power to go as k to the minus alpha, and we have taken the square root of it because that's the way the amplitude should go, right? A and B have unit standard deviation. And so we have generated something here, okay, which describes, through A and B being Gaussian random variables, the randomness associated with the process and the overall the power pattern that it should follow as a function of k. A and B being independent Gaussian variates ensures that tan inverse of B by A follows uniform distribution. The standard deviation. It ensures that the A square plus B square follows exponential distribution given by the twice with the mean given by twice sigma square. So this, and so you can populate all kx and ky's, okay, with the contribution coming from independent A's and B's. Each time for each value of k, you will have new A and B, but the k, which is not square root of kx square plus ky square, okay, that is given by the index of k and ky, kx and ky. That's not random. Alpha is not random. Alpha is something that you have chosen, okay, as a description, which could be a Kolmogorov spectrum, in which case it will have some specific values. You could have red spectrum, in which case alpha is positive. You can have blue spectrum, which might make, or you can even have a white spectrum where alpha is equal to 0. So it's left to you. And this contribution then makes you basically have a full description across a 2D matrix of kx, ky. Then when you Fourier transform, you will get a description if you have kept the Hermitian symmetry in F. That means if you are ensured that f of kx, ky is complex conjugate of of minus kx minus ky. Okay. Then the Fourier transformed result will be only real. But if you have not enforced this condition, and each kx and ky, regardless of whether it's has an independent contribution, then you will find that the resultant output will be complex, and you will have two realizations for the price of one Fourier transform, which you can use if you wanted many such realizations. They will provide you two realizations readily. Of course, it's not some great benefit, because you already used, if you use this fact, you use less number of Gaussian realizations, and you're getting only one. If you use double the number, you will get two descriptions. So there is no violation of, you're not getting something free for nothing. It's tied up with how much information you have put in one domain, results in independent pieces of information in the other domain. So I would encourage you to try this out and use this as a powerful tool of generating random screens following certain description, which might be of interest to you given the physical context, like random media, that you encounter many times. If you want to see how, given the phase perturbation of the wavefront across the wavefront has led to certain seeing conditions and so on and so forth, all those can be simulated, but for which you require some description, and it should be random enough of the screen playing the spoil sport. So this will provide you that. So thank you. If you have any questions, I'll be happy to answer. So I've given you a recipe for generating random distributions. Which you can use in tandem with whatever we have described. And so this can form your input. Fourier transform of this will form your input to the kind of software or program that you might develop in Python to get the azimuthal average profiles in log, and then you should see this behavior standing out. Of course, when you plot power as a function of k, the description will follow actually k to the power minus alpha because of the squaring.
Any comments, questions? Yeah. Yes. So I think Najam has already shared with the participants the Jupyter notebook, which he has worked on.
Basic.
Okay.
It's the basic stuff. So I hope they can, use that as a starting point and go ahead
Yes.
and the things you've been talking about, because I think that's when the fun will come.
Okay. Yeah, that's good.
Yeah.
I think so. We have completed the full loop. Okay.
Yeah.
Of spatial frequency domain descriptions, and just I cannot resist mentioning something in the lighter vein when Sunita Nair, I think was, I think it was Sarup's 60th birthday or 65th birthday, and she presented him a picture which was done in the following way. She took his real picture, Fourier transformed it, and then kept, of course, the Fourier description was, completely spanning the entire spatial frequency domain. She kept only the measurements which the GMRT would do in terms of, symbolically during a 12-hour run or a given direction and so on. And this is like the way in reality when we have sky coming from some patch of the sky, which is to be imaged. The GMRT would look at it over several hours and measure various Fourier components of that distribution, and then put them together to make an image. And that's what she had done. So she had used the mask of the 1-0 mask in the spatial frequency corresponding to the GMRT. Fourier transformed it back to see what image you would get. So I would encourage you to do that here as well. The second part I would like to encourage you to do is to appreciate, may not be possible in here, but in general, if you had, in general, any description in one of the domains, if you saturate the information to either just dark white or dark black, okay, just two states, just black and white, single bit information instead of having any grayscale, you will find that it captures pretty much most of the information relating to the spectrum, which people use in signal processing as one bitting, or just using the sign of the signal, not worrying about the amplitude. So you can do that and see that it actually captures much of the essence of information that is available in the image. This, of course, boils down to the, underlying the importance of phase information as against the amplitude information. So if at all somebody asks you to sacrifice some information because of some compression one wants to do, one can ask which information I would give up on or give away, but which I will not, and which information I will hold as a necessary piece of information. And that is the phase information. That is the information really that is there in the sequence, how things are going up and down or from black to white and so on. It's not important whether it goes to extreme white or extreme black or somewhere in between. That the transitions are more important. Okay.
Yeah. So thank you so much for that conversation. And thank you. And
okay, if there are any questions, and I think your school runs for another day or two, right? Another day, maybe.
So there's a request for the PPT, which you just showed. So if you mail it to me, I'll share it with the participants.
Oh, which PPT?
Just now what you showed, right? That was the notebook. You showed the notebook, right? Huh? Yeah, the plots which you showed today.
Oh, some of the plot. Okay, those are, okay, I will, I will share it with you.
Yeah.
Those are, but I cannot guarantee you the correctness of anything there. Okay, these are things that are put together by the students, okay, for presenting it to somebody. And
Okay.
so take it with that pinch of salt. This is not my PPT. So I cannot take any guarantee of the correctness. Even the conceptual, gaps might exist, and I don't want to, propagate them. So that's,
Yes.
I will certainly make it available to you. Use it with the discretion. Okay.
Okay. Okay, no problem. Yeah. So thanks
Not
a
as a
lot.
guide, but imagine as somebody else's similar notes as they were listening to it, or jotting things down, or trying to describe it in the way they understood it.
Yeah.
Okay, great.
Okay. So thanks a lot. Thank you.